Science is built on sharing. But what happens when the information itself becomes the hazard? When publishing detailed methods for a pathogen experiment could enable the next pandemic? Or when describing a toxin mechanism might teach someone how to weaponize it? This is the info hazard problem, and it is one of the most pressing challenges in modern science communication. Today, we explore how Bioscreens applies Bostrom's information hazard taxonomy to help scientists share knowledge safely. An information hazard, or info hazard, is information that, when communicated or published, causes or enables harm. This concept, formalized by philosopher Nick Bostrom in 2011, goes beyond traditional censorship debates. It recognizes that the information itself, independent of any physical agent, can be the dangerous payload. A synthesis route. A mutation that increases transmissibility. A protocol that bypasses biosafety screens. The danger is not who publishes it, but what the information enables in the hands of anyone who reads it. In 2011, Oxford philosopher Nick Bostrom published a landmark paper taxonomizing information hazards into 11 distinct types. His framework recognized that harm from information operates through multiple pathways, from the direct transfer of dangerous knowledge, to subtle shifts in beliefs or attention that could cascade into catastrophe. Bostrom distinguished between hazards based on who is harmed, how the harm is mediated, and whether the information directly enables harm or sets conditions for it through second-order effects. The four most relevant categories for biosecurity are: first, data hazards, which are raw sequences or synthesis routes that directly enable pathogen construction. Second, idea hazards, which are conceptual frameworks that reveal new attack vectors even without specific technical details. Third, competence hazards, meaning information that brings a non-expert closer to executing a dangerous act. And fourth, template hazards, which are protocols or methods that can be directly copied to produce harmful agents. Science communication triggers different hazard types depending on how specific, actionable, and accessible the information is. The science communicator faces a genuine dilemma. On one side, openness. Science depends on reproducibility, peer review, and the global sharing of findings. Restricting information limits scientific progress and breaks the social contract of open inquiry. On the other side, responsibility. Some information, once public, cannot be unshared. The dual-use dilemma is particularly sharp in biology, where the line between understanding a pathogen to defend against it and enabling its weaponization can be a single paragraph of methods. Bioscreens is a computational framework designed to detect info-hazard content in scientific manuscripts before publication. Applying Bostrom's taxonomy as a structured classifier, it evaluates text, figures, and supplementary data to flag content that meets info-hazard criteria. Rather than a binary pass-fail, Bioscreens produces a hazard profile, a structured assessment that tells researchers which specific categories of risk are present, how actionable the content is, and what targeted redactions could resolve the concern while preserving the scientific contribution. The Bioscreens detection pipeline operates in 4 stages. First, ingestion. The manuscript is parsed into text, figures, tables, and supplementary materials. Second, entity recognition. Biological agents, chemical entities, protocols, and sequences are identified using biomedical natural language processing. Third, hazard classification. Each entity is evaluated against Bostrom's taxonomy to assign hazard type and severity. Fourth, Redaction recommendation: the system generates specific, targeted suggestions about which sequences to mask, which protocol steps to generalize, and which figures to modify, while preserving the paper's scientific integrity. Consider 3 scenarios bioscreens might encounter. First, a virology paper including the full genomic sequence of a gain-of-function variant, flagged as a data hazard, with a recommendation to deposit the sequence in a restricted access database and cite an accession number instead. Second, a structural biology paper revealing the precise binding pocket of a toxin, flagged as an idea hazard, with a suggestion to describe the mechanism at the class level. Third, a biosynthesis paper providing a complete de novo synthesis protocol, the highest severity alert, recommending consultation with a biosafety officer before publication. Based on bioscreens analysis and Bostrom's framework, safe science communication follows 4 principles. First, separate the finding from the enabling detail. Publish what you discovered without publishing exactly how to replicate the dangerous part. Second, use restricted access repositories for sequences and protocols that must exist in scientific record. Third, engage biosafety officers early, not as gatekeepers but as co-designers of the communication strategy. And fourth, apply the counterfactual test. If this information were not published, how much would it meaningfully delay a sophisticated adversary? The future of safe science communication lies at the intersection of 3 systems: AI detection tools like bioscreens that can screen content faster than any human review panel, governance frameworks that encode Bostrom's taxonomy into journal editorial policies and preprint server filters, and community norms among scientists themselves, who increasingly recognize that biosecurity is part of their professional responsibility. These 3 systems reinforce each other. Better AI detection informs better policy, which shapes community norms, which generates better labeled training data for the next generation of detection tools. The infohazard problem will not be solved by silence. The scientific community cannot simply stop publishing biology. But it can publish more thoughtfully, guided by frameworks like Bostrom's taxonomy and tools like bioscreens. The goal is not to hide knowledge, but to be intentional about which details are shared, in which forums, with what access controls, so that the life-saving potential of biological research is not neutralized by the risks it inadvertently creates. Science communicators, journal editors, and researchers all have a role in making this the new norm.